Welcome back to quantitative reasoning. Computers, unlike humans, don't mind repeating tasks over and over again. Syntactic features of a programming language that cause a computer to repeat one or several instructions are called loops. R has different types of loops suitable for different applications. Starting with tutorial 7, we've already seen many instances where vectorization carries out a repeated task. For example, in the command C 2,4,7,6 plus C 5,7,3,9, the vectorized plus operator carries out a loop over the 4 elements in each argument. In each iteration, that is, for each element in the loop, R carries out one addition. Some pre-installed functions also implicitly execute loops. For example, we can simulate 10 rolls of a die with sample 6 size equals 10, replace equals true. In this case, the loop has 10 iterations, namely one for each die roll. Vectorized operators and pre-installed functions are in fact the fastest and most elegant techniques to implement loops in R. But there are limits to these techniques when we want to iterate complex procedures. In this chapter, we learn how to cope with such situations by using for loops. We can use a for loop when we have a vector, say v, and want to perform some action for each of v's elements. The general syntax is as follows: for, open parenthesis, I in v, close parenthesis, open curly brace, commands to be repeated for all values I in v, close curly brace. Here is a simple example of a for loop. For I in C, our, first, for loop, and in curly braces, print, in parentheses, I. In the code block between the curly braces, I is given the values in the vector C, our, first, for loop, one after another from the first to the last element. The command print, in parentheses, I shows the value of I in each iteration as console output. We don't need to give the iterator variable the name I, as long as we consistently change its name everywhere in the for loop. For example, we may want to replace I by the more descriptive variable name word. The code produces the same output as before. We can also do more interesting things than printing out all values. For example, we can repeat simulations of a random experiment to estimate the probability of certain outcomes. Let's consider drawing 5 random cards from a standard deck of 52 poker cards. The deck contains 13 cards from each of the 4 suits: diamonds, clubs, spades, and hearts. How many different suits do we get in a random draw of 5 cards? Let's simulate the draws with R and tally the results. We first generate a deck of cards with a wrap function from our previous tutorial. Cards gets wrap C, diamonds, clubs, spades, hearts, 13. Then we initialize a vector OBS of length 4, in which we count how often the 4 possible outcomes occur when we repeatedly draw cards randomly. That is, OBS, in square brackets n, stores the number of trials in which we draw n different suits. We can initialize OBS with rep, in parentheses 0,4, or numeric, in parentheses 4, to ensure that we start counting from 0. The next code element is a for loop, in which we repeatedly draw 5 random cards. If we want to repeat the random draw 10,000 times, we can start the for loop with for, in parentheses, I in 1:10,000. In each of the 10,000 iterations, we draw 5 cards and count the number of suits. Let's call this number n. At the end of each iteration, we increment the number of observations of n by 1. After the for loop, we can view the result, for example as a bar chart of the relative frequencies stored in OBS. While we're learning for loops, we may find it useful to describe the steps in natural language before we translate each step into computer code. Let's start by translating our first comment inside the curly braces. We can simulate a random draw with sample, in parentheses, cards, 5. For later convenience, we store the sample in a variable called s. Next, we need to count the number of unique values in s. If we apply the length function to this vector, we obtain the number n that we are looking for. Finally, we add 1 to the number of observations of n. The estimated probabilities are in good agreement with the exact probabilities that can be derived with combinatoric arguments. If you're curious, you can find a derivation at the link below this video. One might argue that estimating the probabilities with computer simulations doesn't add new insight if the exact probabilities are already known. However, there are many other random experiments for which the probabilities of the outcomes are unknown. In such cases, it's common practice to resort to computer simulations that contain for loops. In the scientific literature, computer simulations that involve random numbers are called Monte Carlo simulations. Below this video, you can find a link to a paper that describes the historical events that led to the invention of the Monte Carlo method. Most for loops only work correctly if certain variables are properly initialized. In our example, OBS must contain 4 zeros before the for loop gets underway. If OBS isn't initialized before entering the for loop, we get errors or nonsensical results. Whenever you work with a for loop, ask yourself whether any variable that appears inside the loop needs to be initialized. If yes, then don't run the for loop without the initialization. It's usually safer to run the entire script by clicking the source button instead of running only selected lines with the run button. For loops are easier to read if we indent the lines between the curly braces. The indentation shows that these lines play a special role. They contain the commands that are repeated during the loop. The RStudio editor usually does a good job indenting lines correctly while we're typing. If there's something wrong with the indentation, we can select the entire script with the keyboard shortcut Command-A on a Mac or Control-A on Windows or Linux. We then indent all lines with the keyboard shortcut Command-I or Control-I. If the indentation still looks wrong, we probably made a typo. In this case, we must carefully check whether parentheses or curly braces appear in the correct places. If your for loop doesn't work as intended, even after fixing the obvious typos, don't despair. Even experienced programmers regularly make mistakes when writing for loops from scratch. In our next tutorial, I show you a few basic techniques to trace mistakes. Let's recap what we learned about for loops. We use for loops to repeat commands in an R script. For loops should be used sparingly. Vectorized operators and pre-installed functions are almost always better options. A typical use case for a for loop is a simulation of a random experiment. The syntax of a for loop is for, in parentheses I in V, in curly braces, commands to be repeated for all values I in V. We should indent the commands between the curly braces so that it's easy to see which commands are repeated. We must often initialize some variables before a for loop, for example, variables that count how often certain outcomes occur during the loop. We can avoid accidentally leaving out initializations by clicking source instead of run. Next time, we go on a bug hunt. See you soon.